would anyone say for certain that that is an isosceles triangle? Okay, let's put some points in here though. I know that this point is some number away from the origin for x. Let's just call it h. And isn't its y coordinate 0? If it was going to be there. And then let's say over here, I tell you this coordinate right here is the opposite of h, 0. You with me so far? And then this point up here, we know its x coordinate is 0. We don't know its y coordinate, do we? I suppose we could just call it y if we wanted to, but maybe I'll call it k, just for something different. Is that an isosceles triangle? Who says yes? Who says no? Who says isosceles triangle? Anyone? No? Oh, okay. So we know it's an isosceles triangle if the legs are the same length, right? So if this length right here and this length right here, if they're the same length, then this would be an isosceles triangle. Or I suppose the angles, although the angles might be a little tough at this point. Can we prove that that segment and this segment, can we prove they're congruent? I mean, how do you know two segments are the same length?
Well, in that case, they have like opposite slopes.
Oh, I think that would tell us if they're parallel or something, right?
Well, not opposite reciprocals, there's opposite.
So that would tell us about the. You might be able to use that for an angle thing, but the lengths of the actual segments. I don't know. Yes.
They meet at the same point and they're the same distance away from the y-axis.
Yeah, that is very true. That is very, very true. Yes.
Distance one.
The distance formula. Dang, someone's on it today. Good job. That's how we tell. In a coordinate plane, we want to know if two segments are the same length. We use the distance formula. Okay. Now it's really weird here because we don't have a whole lot going on to use the distance formula, but we can still do it. So the length of this segment right here would be the square root of its x coordinate, subtract this one's x coordinate, correct? Okay, 0 squared, plus its y coordinate, subtract the other point's y coordinate, squared. And so let's make this a little better here. The opposite of h, subtract 0, is simply the opposite of h, squared. And then 0 subtract k is the opposite of k squared. And then what happens when you square them? Okay, so the opposite of h squared and h squared, is there any difference? No, it's the same thing. And the opposite of k squared and k squared, they're the same thing, aren't they? Okay. Well, let's look at the length of this other segment over here. Square root of, parentheses, plus parentheses, squared, squared. Got to. Do you guys do it that way and then just put the numbers in, or do you do it a little bit at a time? Okay. So it's x, the x coordinate, h minus 8 or 0. So h subtract 0, and then 0 subtract k. And so we end up with the square root of h squared plus the opposite of k squared, which is the square root of h squared plus k squared. Now we don't know what the square root of h squared plus k squared is, but we do know that those two segments have the same measure. They're both the square root of h squared plus k squared, aren't they? Okay? So, they're congruent. This is an isosceles triangle. This is what we would call a coordinate proof. We're placing a figure in the coordinate system, and we're using some of the tools we have to do a proof. And some of the tools we have, he is the guardian of these tools. One of them is the distance formula, and the other one is the midpoint formula. Okay? The midpoint formula says, okay, if this is the midpoint, then, you know, what's the definition of a midpoint? What does it do? Divides the segment into two congruent parts, doesn't it? So when I say, you know, this is the midpoint, I'm saying this segment and this segment are congruent. Okay, so it lets us know that. So this is what we're going to talk about today, is coordinate proofs. Turn to page 284. Okay. First of all, we're going to talk about placing a figure in the coordinate plane. I didn't just place that figure anywhere. Did I? I didn't just choose some random place to place this figure. I mean, I put it in a place that was convenient, that made my life easier. For example, on an axis. Why would I ever want to put the points of a figure on the axes? Yeah, I get zeros, which are easy to deal with, aren't they? Okay? So placing it like that. And you know what? If you can take a figure and put one of its vertices right there, the origin, 0, 0, how's that going to work out in the distance formula and the midpoint formula? That's going to make things good, isn't it? Okay? So when we place a figure in the coordinate plane, the first thing you need to understand is we don't just place it willy-nilly. We put it in a place that makes our lives the easiest. Okay? So take a look at example 1. You see they have a rectangle placed in the coordinate plane. Where did they put one of the vertices of that rectangle? On the origin. And two of them are, one's on the y-axis, one's on the x-axis, and then the fourth one, of course, has to be out there at HK, but at least, you know, not too bad. And then the other triangle, you notice they put one of its vertices at the origin, the other one on the x-axis, and then only one of the vertices is that FG. And so it's important to try to place the figure in a way that makes it convenient, let's say. Okay? So let's go down now to example 2. Writing a plan for a coordinate proof. Okay. So take a look at the figure. We got a triangle in the coordinate plane. It looks like it's triangle PSR, and it tells us the actual locations of those vertices. And it says prove that ray SO bisects angle PSR. Ooh, prove that it bisects the angle. Okay, so -3, 0, 3, 0, and 0, 4. Right here we have point O, which is 0, 0. Prove that it's an angle bisector. How do you know if something's an angle bisector? I mean, if I just had an angle and I had this ray sticking out here like this, how would you know that that ray is an angle bisector? Okay, so if I told you this one was congruent and to this one, Would you know it's an angle bisector? Okay, so that's it. We've got to prove that this angle right here is congruent to that angle right there. Now you're looking at them like they're kind of in, it's one triangle. I want you to look at the two triangles. See the two triangles? That one right there? And this one right here. In those two triangles, would you say that these two angles are congruent? How do you know that? How do you know that two angles in two different triangles are going to be congruent? How can you prove that? Like if I gave you two triangles and said, prove these two angles are congruent, what would your final reason be? What is that? That's it. They're corresponding parts of congruent triangles are congruent. They are corresponding parts of congruent triangles, aren't they? Okay. We think that these two triangles are congruent. Can we prove they're congruent? Well, heck yeah. I'm going to say PO, that segment, is congruent to RO. What's my reason? Distance formula. Now, did anybody see me actually use the distance formula? No? That one's 3 units long and that one's 3 units long, right? Okay, so, but we don't just say that. We say, oh, I use the distance formula and they're congruent. But we can look at them and know, can't we? Okay. What about SO? Oh, it's congruent to itself. Heck yeah. So that's the reflexive property of congruent segments. Now, what about PS and RS? Are they congruent? How do you know? Distance formula. We can use the distance formula on them. Even if you use the Pythagorean theorem, even if you go 3 squared plus 4 squared, yeah? You with me here? Okay. Even if you say 3 squared plus 4 squared equals 5 squared, remember that Pythagorean triple? Okay. Even then, you still say, I use the distance formula. Now, I'm not going to use the distance formula in this case because, look, the Pythagorean theorem is so much nicer, isn't it? And aren't they the same thing anyway? Okay. So we're going to say that PS is congruent to RS. What's our reason? Distance formula. Okay. So now I can say, okay, triangle PSO is congruent to triangle RSO. How? How do we do it? Side, side, side. We proved all 3 sides were congruent, right? And then we can say these 2 angles are congruent because their corresponding parts of congruent triangles are congruent. And then we can say this is an angle bisector because that's the definition of an angle bisector, right? When we say these 2 angles are congruent, that's what an angle bisector does. It divides the angle into 2 equal parts, doesn't it? Definition of angle bisector. Plan? Do we have a plan? Now, this is not a full proof here, is it? But it's a plan. Okay, and that's what we were asked to do. Okay, everybody turn to page 285 and look at example 3 right at the top. I'm going to draw it while you guys think about it there for a minute. And then I'm going to call on one of you and ask for your plan. Did that make all of you a little frightened there? Think. Notice when it said that this segment, GJ, bisects the angle, I actually marked those two congruent. Isn't that the definition of a angle bisector, right? Okay, so don't fail to do that. You want to think about that, right? So prove triangle GJO and GHJ here that they're congruent. So who's got a plan? Yeah, few. I see 4 of you that seem like I have a plan. Cheyenne, you got a plan?
I guess so.
Let's hear it.
So we'll prove that EJ is congruent to itself, and then we'll
How?
with reflective property.
Oh, that's, yeah, obviously. Good job. Yes, keep going.
And then GH and OD are congruent because of distance formula.
Okay, so you can use the distance formula to show that those two are congruent,
And
and that's all we need to do, because then what do we have? Side angle side. Oh man, I cannot tell you how much I was hoping that someone would say, prove this one was congruent to itself by the reflexive property, and then use the distance formula to show that JO and JH were congruent, and then use angle side side. You could do that if angle side side was a proof of congruence. But does angle side side always work?
No.
Only when? Only in right triangles for hypotenuse leg. So did anybody think that and then think, oh wait, that's angle side side? Is anyone glad I didn't call on them? Yeah, okay. So it's kind of weird because in this case it seems like angle side side should work, shouldn't it? I mean, they are congruent, aren't they? And that is the weird thing about that one, is that it works sometimes. Okay, so here's a case where it works, but did I show you a case where it didn't? Remember that one? Okay, so you just can't rely on it unless you have some other information. Awesome. Yeah, you guys are doing great today. Okay. Applying variable coordinates. So this one, we knew the actual coordinates. We had numbers here, right? What if we don't? And I actually showed you this one already. So down on example 3, you'll notice that some of the coordinates for the endpoints of that triangle are not definite. You know, point Q is at K0. You know, what's K? Doesn't matter. Doesn't matter what K is, right? Because point P is at 0K. As long as O is at some number 0 and P is at 0, that same number, K in this case, right? Those two segments are going to be congruent, aren't they? Got a lot of blank stares on that one. Yes? Yes. Okay. So, got our coordinate system here. I've got this point over here, and I'm going to call it K0. I got this point over here. No, this is going to tick you off. I'm going to call it 0K. Are this segment and this segment congruent? Yes, they are. Do they look congruent in my picture? No, my picture sucks. But it doesn't matter. If this one's at K0 and this one's at 0K, those segments are the same length. No matter how badly I draw them. And I've seen your homework before. Right? Okay. All right. Let's turn over and make you cry a little bit. Let's look at example 4. Take a look at it. looks like a parallelogram with the diagonal drawn in. Some of the vertices like O and V aren't too bad. Point T isn't horrible, MK. Point U, M plus HK. Not fantastic. We're supposed to prove that triangle OTU. You guys find that one? That's the one on top. And UVO are congruent. Those. So we've got OU congruent to itself by the reflexive property. Everybody good with that? Okay. However, we need more than that. Do you think that we could find the measure of OT? Can we figure out how long that one is? We can. We can use the distance formula. Okay. So, ready? 0 subtract what? What? M squared plus 0 subtract K squared. And do you guys get how this just boils down to M squared plus K squared? Do I need to go through the whole thing again? Okay, we got that. Now, let's think about the measure of its counterpart. So that was OT. What does that correspond to in the other triangle? Isn't it VU? VU, right? So now we want to find the measure of VU. All right. So let's start. We're starting at V. X coordinate H, subtract the x coordinate of U, right? Now this is some algebra right here. You have to subtract M plus K. Not just M, you have to subtract the whole thing. All right? And then we have to add. Okay, let's look at the y coordinates. Isn't that one just 0 subtract what? K. Squared. So let's think about this again. When we remove this parenthesis, see, we're going to subtract the entire quantity. It turns out to be H subtract M subtract H squared. You see it?
No.
Okay. So right here, I'm subtracting this x coordinate. The x coordinate is M plus H, right? So if I subtract M plus H, I can't just subtract the first term of that system. I have to subtract the entire quantity. And if there's a subtraction symbol in front, what is it telling you? You have to subtract M and you have to subtract H. So anytime I have, especially if I have something like M plus H for a variable and I have to substitute it, I replace the variable with parentheses and then I put what it's equal to inside the parentheses so that I don't miss something like that. Then over on the other side, that one's pretty simple. It boils down to K squared, doesn't it? But the important part here is, what's H subtract H?
0.
And what's the opposite of M squared? M squared plus K squared. So, this segment and this segment are congruent by the distance formula. I don't see a single tear out there. I've got to work harder. Down at example 5. You guys all see it? How long is OP? What's its measure? Now, what is the measure of segment OP? What is it? No, not the flower one. Example number 5 down at the bottom. Oh. Oh. Monitoring progress, number 5, coordinate proof. Okay, now everybody look at segment OP. How long is it? What is its measure? 2H. How do you know? The what? Even though you can look at it and just know it's 2H because its x coordinate is 0 and its y coordinate goes from 0 to 2H, you still say that's your reason, okay? So it's 2H units long. How long is OM? How long?
2H.
How do you know? Distance formula, yeah. Are PN and MN congruent? Are those two segments congruent?
Yeah.
How do you know? Yeah. Isn't point N a midpoint?
Yes.
It is a midpoint, isn't it? Okay. If P is at 0, 2H, and M is at 2H, 0, then N is at HH. It's a midpoint, isn't it? So those two segments are congruent. Can you prove those two triangles are congruent by side, side, side?
Yeah.
You can, can't you? You got distance formula, you got definition of a midpoint, and you got the reflexive property. You got side, side, side. You ready for this? This is a long lesson. Here you go. Chapter 5.8.